Okay, so continue now with video 5 for 3.1. We have our continuous compounded interest formula. And so this one, a lot of times, I've heard it referred to as the PERT, because it kind of looks like PERT there. But it's only used when interest is compounded continuously. It has to say continuously compounded, compounded continuously, something like that in order for this formula to work. So A is still the ending amount, P is still your beginning amount, R is still your interest rate as a decimal, and T is still the number of years. Notice E is not listed there because remember E is a number, and you can find that by hitting second LN on your calculator. But E is just a number. It's kind of like pi. All right, so moving on to example 8 then. It says, find the amount when a principal of $8,300 is invested at 7.5% annual rate of interest, compounded continuously for 8 years and 3 months. All right, so I saw compounded continuously, which tells me we're going to use A equals P raised to the RT. Well, it told me the principal is $8,300. It's invested at 7.5%, so that's my rate. Change it to a decimal. Compounded continuously told us our formula for 8 years and 3 months. Well, remember I said time has to be in years, so this is 8 years and 3 months. Well, that's 3 out of 12 months. So that's 8.25 years. All right, so then we're just going to plug it in our formula. We're after the amount. We're after the ending amount. So A equals 8,300 E to the 0.075 times T, which is 8.25. So we can just plug this in our calculator and get our answer. Now be careful because some of y'all may have older calculators. And so if you do, when you type in, and I'm going to just write this below it here. So when you type in, you're going to do 8,300. You're going to hit second LN, and it's going to do E raised to the. Well, if you're lucky, it'll open a parenthesis. Sometimes it doesn't. And then if it doesn't, you need to open it because you're telling it that the 0.075 times the 8.25 goes together in the parenthesis. Notice I did not use, goes together in the exponent. Notice I did not use parentheses to separate them because if I had closed the parenthesis there, my calculator says, oh, that's what you want me to raise the E to. And then I take that answer and multiply it by the 8.25. So that's one reason I use the times symbol. Otherwise, I have to start using double parentheses there because we know that all of that is going to be up in that exponent. All right, so if I get this typed into my calculator correctly, then I should get $15,409.83. All right, and so then we've got our natural exponential function. It's the same thing, but we have a base of E. We don't have a parent table for it. E is irrational. Like I said just a few minutes ago, it's like pi. You know, it never, ever ends. So we don't actually have a parent table for it. If we are graphing with E, we're just going to have to use our calculator. All right, so models for exponential growth and decay. Notice they're very similar. The only difference between them is if it's growth, our K is positive, and if it is decay, then our K is negative. So, example 9 says, in the year 2000, the human population of the world was approximately 6 billion, and the annual rate of growth was about 2.1%. Use the model on the previous slide. Estimate the population of the world in the following years. And so A starts us out in 2030. Well, first thing is they gave me a couple things here I'm going to use for both of them. And so they told me that in year 2000, the population was approximately 6 billion. So we're just going to let that be our beginning amount. So our times 0 will be our year 2000. So our initial amount is going to be 6 billion. And it told us that the growth rate was 2.1%. So that's going to be that K. So K is going to be 0.021 because remember you need to change it. All right, so for A, it tells us to find it in the year 2030. All right, so we know our formula was A of T equals A sub 0 E to the KT. So, but when we're looking in the year 2030, if T equals 0 was a 2000, which is how we got this right here, then we know that 2030, then t is going to be 30. So we're looking for the ending amount 30 years after it started. And so we're going to use our beginning amount 6e to the 0.021, my k, times t, which we just said was 30. And so we can type this in our calculator. And you should get approximately 11.266, and we ought to label it because it's a word problem, and so it's billion people. And then B says, we're going to use the same formula, but now saying in 1990, but the beginning year was 2000, so if I use 1990, then my t is -10. And so I'm going to plug -10 in, so 6e, to my k times my t of -10. And so I can just type this in, and we get approximately 4.864 billion people. Oh, and I just had an extra slide there in case we needed it. And that's it, guys. So that's the end of 3.1. I'm going to go ahead and upload this real quick. I'm going to take a break, and then I will work on 3.2 here in a little bit and try to get that uploaded as soon as possible for you.